We propose DeepPanoContext for panoramic 3D scene understanding with holistic scene context graph and relation-based optimization. 3D scene understanding is very important in many applications like robotics, augmented reality, and mixed reality, where information like room layout, object categories, poses, and 3D geometry are needed in order to interact with the environment. Currently, single-image total 3D scene understanding aim to jointly estimate room layout, oriented object bounding boxes, and object meshes, in order to achieve semantic reconstruction of the scene. Previous works show that context information is very important for scene understanding, but the field of view of perspective camera is limiting the available context. Therefore, we propose to use panoramic camera for total 3D scene understanding, which can provide more context information and complete layout. To be more specific, from a single panoramic RGB image, we aim to achieve full scene reconstruction by jointly estimate room layout under Manhattan world assumption, oriented object bounding boxes, and object meshes. In general, there are two main challenges for our task. Scene context is one of the most important information we want to leverage. Although previous work implicit 3D understanding has tried to learn and exploit relations implicitly, it ignores that well-defined explicit relations, including attachment, support, and rotation, exist in real life. Thus, by naively applying it to panoramic image, the results can severely disobey with explicit relations, which hurts the precision of object pose estimation. For example, the left side of the bed should be closer to the wall, and the cabinet here should be inside the room. Another challenge is that existing panoramic datasets do not have enough ground truth for panoramic 3D scene understanding, especially object mesh. Although total 3D understanding provides a seemingly feasible solution to train modules separately on different datasets, the domain gap between scene understanding and object reconstruction datasets can introduce artifacts in the final reconstruction like in implicit 3D understanding. Thus, a panoramic dataset with complete ground truth is needed. To deal with these challenges, we make following contribution including the first deep learning-based pipeline for holistic panoramic 3D scene understanding, a context model to predict and exploit explicit relations for object pose refinement, and a synthetic dataset with complete ground truth. At high level, our pipeline contains three major steps: a bottom-up initialization, a relation-based graph convolutional network, and a relation optimization. In bottom-up initialization, we use several state-of-the-art methods similar to previous works to provide initial estimation including layout, object poses, and rich features of image, shape, and geometry. In specific, given a single panoramic image, we first estimate whole room layout under Manhattan world assumption with HorizonNet. Then we run a mask RCNN to detect 2D objects. From each object detection, we use an object detection network to generate initial pose, and a local implicit embedding network to generate latent code for each object which embeds its implicit shape. In relation-based graph convolutional network, our goal is to create a scene graph, where each node represents an object or a wall, and each edge represents the relation between adjacent nodes. To do so, from the previous initial estimation, we decompose the layout into walls and embed their features into wall nodes. The image, geometric, and shape features are also embedded into object nodes, to be connected with wall nodes into a graph. Then a relation-based graph convolutional network is used to learn the context information to refine object poses, and estimate the explicit relations of rotation from objects to objects and walls, and explicit relations of attachment and support from objects to objects, walls, floor, and ceiling, all indicated by white lines. With the estimated relations, we run a relation optimization to further optimize the refined object poses. To be more specific, in the relation optimization, we seek to minimize a loss function including three terms of collision, observation, and relation. The first one is the collision term, which measures the amount of collision among objects and layout. For collision between objects, we use separating axis theorem to minimize the separation distances d between two intersected bounding boxes. For collision between objects and 3D layout, we minimize their distances to avoid collisions with walls, ceiling, and floor. The second one is observation term, which measures the deviation from two bottom-up observations. One is the deviation from the refined object pose estimation. Another is the 2D bounding box alignment error, which measures the consistent between the 2D bounding box of a 3D bounding box projection and its detection result. The third one is relation term, which measures the conformity of object poses with regard to the predicted relations from RGCN. With optimization objective defined above, we use a gradient descent to minimize the loss function and optimize the object poses. Please note that our relation optimization module is differentiable, thus can be plugged into the model for training. Finally, the object shapes decoded with shape decoder LDIF are placed into the scene according to the optimized object poses to get the final scene reconstruction. To train and evaluate our model, we present a new synthetic dataset for panoramic 3D scene understanding based on I-Gibson, which provides RGB input and the ground truth of 2D object bounding boxes, bounding field of views, masks, 3D object bounding boxes, object shapes, layout, depth map, instance segmentation, semantic segmentation, and pairwise relations of attachment, support, rotation. We generate 1500 images for training and evaluation, and the code is released for generating more images. Also, we render object-centric images from object models used for single-image object reconstruction and make their models watertight for training implicit representation network. Here we show our results. In quantitative comparison, we compare to the state-of-the-art 3D scene understanding methods, including total 3D understanding and implicit 3D understanding, on 3D object detection with mean average precision, or MAP. By dividing the panorama camera into a set of cameras with horizontal FOV of 60 degrees, we enable previous 3D scene understanding methods on perspective image to work with panorama images. Besides the perspective version, we also extend previous works to work directly on panorama images. Our method has a great improvement over the state-of-the-art even without relation optimization. With it, the result is even better. We also fine-tune our model up to RGCN on structured 3D and compare on 3D object detection. The results show that our method still outperforms state-of-the-art methods significantly, and RO plays a big role in improving the MAP. To highlight the improvement benefit from relation optimization on collision avoidance, we calculate average collision times among objects per scene and the average number of objects colliding with objects, ceiling, floor, and walls. Our method outperforms state-of-the-art methods from all perspectives in preventing physical collision, while the gap from the ablated version further illustrates the importance of relation optimization. The example here shows how our method outperforms previous methods in terms of preventing collision with walls. In qualitative comparison, our method achieves best result on 3D-2D correspondence thanks to relation optimization. We also achieve more reasonable object-wall relations looking from the bird's eye view. For example, our method aligns the bed closer to the wall like in ground truth and places the cabinet more accurately on the wall. Here we show more examples. In this example, our method hangs the picture correctly on the wall and places the door close to the wall. In this scene with some hard cases like distant objects, our method can leverage the predicted attachment relation to better align the table with the room corner and better estimate the distance. The position of desk and the window here also show better relations to the wall thanks to our relation-based model. In this much simpler case, even the 3D-2D correspondence is quite good in previous methods, they still fail to estimate the right distance for each of these doors. To evaluate different terms of the proposed relation optimization, we conduct ablation studies by removing each of them from our method and make comparisons on 3D object detection and physical violation. We compare 3D object detection with MAP on all categories and physical violation with average collision times per scene. By removing relation optimization, we observe a great drop on both metrics. The missing of collision term hurts the average collision times the most, which illustrates its importance on collision avoidance. The missing of relation term hurts the MAP, which shows that relations are important on the improvement of 3D detection. We observe even greater drop on MAP when removing observation term. This shows that bottom-up observations help 3D object detection by constraining object poses with initial estimation and reprojection. Finally, it is interesting to see that not a single one term can be removed for our model to work, showing that our proposed terms collaborate to improve 3D detection. We also visualize the optimization process of our ablated models on an example scene to illustrate how each term helps. Here, we show the ground truth object bounding boxes in gray for reference. For demonstration, we add random noises to the ground truth object poses as the initial state, which simulates the inaccuracy of the initial pose estimation. The attachment and support relations are indicated by white lines, while the collisions are highlighted in red. First, we show the optimization process of our full model. Then let's see how optimization goes without certain terms. By removing the collision term, more collisions, indicated as red lines, are remained in the optimized result. For the ablated model without relation term, the relative object rotation and attachment relations are less obeyed. Finally, the missing of observation term causes less overlap between the reprojected bounding box estimation and the ground truth. In order to further evaluate the proposed relation optimization, we apply our RO on total 3D understanding and implicit 3D understanding using our predicted relation to optimize their final results. We can see that both methods still significantly benefit from the RO, which demonstrates that our RO is effective and robust to different initial estimates. To learn the effect of wide field of view of panorama, we conduct ablation experiments on our proposed method by splitting the panorama into different FOV. We compare our full model, with or without RO, with MAP on full 57 categories. The results show that limiting the message flow within small FOV hurts the performance, which means that our model is really taking advantage of the whole scene context to estimate object poses. In summary, we propose the first deep learning-based pipeline for holistic 3D scene understanding that recovers 3D room layout and detailed shape, pose, location for objects in the scene from a single color full-view panorama image. To fully exploit context, we design a novel context model that predicts the relationship among objects and room layout, followed by a new differentiable relationship-based optimization module to refine the initial results. To learn and evaluate our model, a new dataset is created for total panoramic 3D scene understanding. Our model achieves the state-of-the-art performance on both geometry accuracy and 3D object arrangement. Our code, pre-trained models are available online. Thank you.